Yeah, it doesn't really matter, Nick. I mean, typically if it's parametric, it's gonna be a vector value function. That's typically the way it is. Yeah, no, that's fine. Oh, yeah, that's it. You can still think of that as a parametric equation. All right, all right. What time does class end? 11, so I'm gonna give you guys 40 minutes. I'm gonna give you guys 40 minutes to take the quest. So when should we stop? When should we stop? 10:20, 10:20. What time is it now?
9:45.
9:45. Stop me at 10:15. I'm ADD. I tend to hyper focus, okay? So you stop me. Stop me when? 10:15, 10:15, and we'll take our quest. We'll take our quest then. Okay, I guess just stand up, don't breathe heavy, guys, if you're sick, get the hell out of here, right? I don't want you taking questions. Stretch. Okay, let's sit back down, let's sit back down. Now this is, for many of you, this will be your first paper assignment. And who knows how many months, right? So it's gonna feel weird having a piece of paper in your hand. Just, you'll get back into the rhythm. You'll get back into the rhythm. And part of the reason is so that you don't have a year and a half where you don't take any paper assignment and then suddenly you're thrown back into a regular junior year and you feel like, oh my gosh, I'm getting completely overwhelmed. Okay. Hopefully everybody studied. How many people studied? Okay. How many people looked at flashcards? Anybody look at flashcards? When I say tangent line, you say, great. Okay. When I say tangent line, you say R of C plus T times R prime of C. Okay. So that's kind of where I want to start today. I've got an R of T. I've got a space curve. I've got a vector value function. Looking up there, what's the domain of that vector value function? What's the domain of that vector value function? A to B. And so as time runs between A and B, I'm just kind of imagining that I'm running along this space curve, starting at the left and moving to the right. Now the job of R of T is to position the vector. Does that make sense? Does that make sense? The job of R of C is to position the vector along that curve. Now, because I grew up in the 1960s, and I'm not a scientist, I'm a mathematician, I don't think in meters, okay? You guys have to change that. Your generation must bring the US into the metric system. We look like morons to the rest of the world when we're going to buy 4x8 foot sheets of plywood. Okay, we look like morons. Okay, so enough of that. Let's talk about feet. Okay, let's imagine that I've got a position and I'm going to measure it in feet. I've got a vector, I'm going to measure it in feet. And suppose that I find that R of C equals 2, 7, 3. Now what I'm thinking of is my units here is feet. Describe what that means as far as the engineering is concerned. Describe what that means as far as the physics is concerned. What does that mean? I've got a vector that's 273 feet. What does that mean? What does that mean? What would mean that you would run down the you'd run down the I direction 2 feet, you'd go up the J direction, go down the J direction, and then you go up the K direction, and that would be the point that would be on my space curve, sitting in three-dimensional space. Does this make sense? Does this make sense? Now again, if you guys have gone through calculus and you haven't actually learned the definitions, you'll never be able to do the applications really. Because it's in the definitions where we actually see the applications. We notice that in physics they call R prime, if R's displacement, then R's derivative with respect to time is what quantity? Velocity. And I guess I marked it there, so velocity. Okay, now I'm thinking about what are the units of velocity? What is velocity's purpose? What is velocity's purpose? What does it do? How does it help us? Speed. It tells us roughly how fast we're moving. And the units should be here. R prime of C is the limit is, you guys read it, you'll get your brains going. R prime of C is the limit as of over T minus C. But what are the units of R of T? What are the units of R of T? What are the units of R of T? The units of R of T is, R of T is feet. What are the units of R of C? Feet. What are the units of T and C? Seconds. So what would the units of this vector be? Feet per second. Does that make sense? Does that make sense that that would be a velocity? Does that make sense that that would be a velocity? Now again, I'm going to evaluate my velocity vector, my derivative vector at some point C, and I might get something like 2, 1, 5. I might get this numerical vector coming out. What does that mean? Well, we know the units aren't feet, but it's feet per second. What does this actually mean, this 2, 1, 5? How many people could plot the vector? How many people think they could actually plot the vector? But what does it mean as far as the physics is concerned? Well, the speed can't be, we're moving at 2, 1, 5 feet per second there, Jack. We're moving at, that doesn't make any sense, right? That doesn't make any sense. The speed is not related to what the vector is, but it's related to the norm of the vector. So if I look at the norm of this vector, R prime of C, what would that be equal to? What would that be equal to? I mean, everybody should be able to do it. What would that be equal to? Everybody should be able to do it. What would it be equal to? Square root of 30. So whatever that, get your calculator out, you put that in. And so we're moving. This vector does what? What's the job of this vector? What's the job of this vector? Positions. So we're positioned at this point in three-dimensional space. We're heading in this direction at a speed of, we're heading at this direction in three-dimensional space at a speed of square root of 30 feet per second. Now let's take the second derivative, and you're like, well, Dr. Warren, what's the definition of that? You're like, okay, guys, how do you get the second derivative? Take the derivative of the derivative. So that's exactly the way it's defined. Calculus is about? Yeah, everything's defined in terms of a limit. So we've got the limit as t approaches c. You're like, oh, Dr. Warren, that's just like that. T minus c. Oh, that's just like that. Oh, but now my function's r prime. So now what would the units of the numerator be? What would the units of the numerator be? Feet per second. What are the units of the denominator? Seconds. So what would the units be? Feet per second squared. And is that not the units that we've learned for acceleration? Is that not the units that we've learned for acceleration? Okay, now again, I could plug numbers in, like a c into the second derivative, and maybe I get -1, -2, 3. And the units here are feet per second squared. This would again be another vector. Could you plot the vector? Could you plot the vector? This position physically is a little bit more difficult than this one. What it's describing is how this vector is changing. What did I just say? It's describing how the tangent vector is changing. Say that. So what's the job of R of C? Dr. Warren, I hate you. What's the job of R of C? Position. What's the job of R prime of C? Velocity. Which direction are you moving in? And how fast are you moving? Does that seem important? Does that seem important? This vector is describing how your velocity is changing. So it's describing how the position you're going in is changing. So I like to think of it like this, and you guys can too. I like to think of how the curve is curving. In the same way concavity, remember concavity back in Calc 1, describes how much that thing is curving. Concave up means smiling. I was smiling and I'm like, holy hell, I got a mask on, I can't see that. Okay, never has that not worked, okay? Concave down is, guess what I'm doing under the mask right now? Guess what I'm doing under the mask right now? Frowning, yeah. So in the same way, your second derivative kind of points, focus, your second derivative points in the direction the curve is curving. So as you're flying along your space curve, the velocity points in the direction you're going and how fast you're going. The acceleration points in the direction you're curving and how fast you're curving around that direction. Is essentially how that velocity is changing. Okay, does this make sense? Does this make sense physical? Do you guys see how this might have some merit? Do you see how this might have some merit? Newton's laws are force equals mass times acceleration. Force equals mass times acceleration. Okay, they're only valid in an inertial reference frame. Say that. What's the key word? Inertial. What does inert mean? Static. What does static mean? Got one in the class I got to take in engineering. Statics and dynamics. What does static mean? Not moving. Not moving. So basically, we like to think of I, J, and K. We think of I, J, and K as being our inertial reference frame. Write that down. We think of I, J, and K as being our inertial reference frame. We think of it as not moving. It's our frame of reference that we refer back to. And did I ask if you guys went to Busch Gardens? Did I ask this class if you went to Busch Gardens? Okay, and did I ask if your mom sat beside the roller coaster? So again, the person up here on the roller coaster, on the space curve we've created, is going to feel something completely different than the person observing from down here. Does that make sense? So as nice as I, J, and K are, they're not great for describing what's taking place up here in our current configuration flying along the space curve. We need a different basis to describe what's happening up along our space curve. So I want to come up with a brand new set of three vectors. I want them to be almost like I, J, and K, except they're going to move. They're not going to be inert. Is it nice that I, J, and K are unit length? Like if you're using them to measure something. Is it nice that I's length is 1, J's length is 1, and K's length is 1? Is it also nice when you're kind of using them to measure that they're all at 90-degree angles to each other? Is that kind of nice? You're like, oh, just go straight out that way, and then you go straight that way, and then you go straight that way. Is that nice? Is that nice? We want those same properties. We want those same properties for our frame that's going to move along our space curve. Now here's the thing. This is inert. The new frame is going to move with the space curve. And that's what makes it hard. It changes as time changes. It changes as time changes. I just feel it. I feel the boredom just floating around the room. I just see it. It's like an evil spirit. Get your hands out, get your hands out, get your hands out. You're going to cast the evil spirit of boredom out of here before you take your quest. Are you ready? Are you ready? On 3, we're just going to go, woo! But don't do that too loud. We're going to keep all the breath in our, ready? 1, 2, 3, go. Woo! Go, evil spirit of boredom, get out. Evil spirit of boredom, get out. Say, evil spirit of boredom, get out. Evil spirit of boredom, get out. Say, I cast you out, evil spirit of boredom. I cast you out, evil spirit of boredom. Okay, I think that failed, but I guess we'll find out. Okay, next. Would it make sense that one of the vectors, maybe the vector like playing the role of I, if I'm just trying, I know no matter what I say, nobody's going to listen. Does it make sense does it make sense that if we're trying to model how this thing's flying in the air, that one of those vectors might point along the direction of the velocity vector, might point in the direction that the curve is curving, I mean, the direction that we're moving. Does that make sense?
Yeah.
And so let's do that. Let's make one of our vectors point in the direction of r prime. Now, does r prime always going to be a unit vector? Is r prime always going to be a unit vector? Are you always going to be moving at 1 mile an hour? No, we can certainly hope not. Even though that's the way my mother drives. Has anybody driven with their mother before? I guess maybe it's different. Does anybody's else's mother drive slow? Does anybody else's mother drive slow? Cosmo's like, no, man. My mom drives a big Anybody mother drive a Suburban? Anybody's mother in here drive a Suburban? I mean, I thought they were invincible in that thing. They thought it was a tank. I mean, it should have just been like an Abrams tank. Okay, well, enough. Let's throttle her back. How do you make a vector into a unit vector? What? Divide it by its norm. So let's make this into a unit vector that points in the same direction that we're moving. And we'll call that capital T of t. And so capital T of t would be equal to what? Write down what's in your brain. Instead of just scribing, write down what you think the answer will be. If you're wrong, it doesn't matter. It's okay to be wrong. Except on the question. I'm gonna play singles with somebody in here. Cosmo, what do you got?
R prime over the norm of R prime.
R prime of t over the norm of R prime of t. How do you get the norm of a vector again, guys? How do you get the norm of a vector? Yeah, take the square root of each of the components squared. Now here's the thing. Is R prime going to have 3 different vector value functions? Yeah, and in general, when you take the derivative of functions, they don't get better, they get worse. And then you're going to take the square root of all of those squared. Could that be a nasty vector value function? Could that be a nasty vector value function? And in general, it is a very nasty vector value function. Okay, what's the norm of t of t? We just made this happen. What's the norm of t of t? We just turned it into a unit vector. That's a big hint. What's the norm of t of t? 1. And this is for every t. This is for every t. Now imagine my arm here is unit 1. Imagine it's length 1. This is a vector. This is a vector. Okay, now imagine it's always length 1. So no matter where I go in the room, this isn't changing. This isn't changing where my elbow is, but this is changing. My hand's drawing a curve on a what? My hand's drawing, the end of my finger is drawing a curve on a what? On a sphere. What do we know about the relationship between radii and tangents? If we're thinking about spherical objects or circular objects. They're always perpendicular. So my position vector, if I've got a unit vector, is always going to be perpendicular to its tangent vector. So if I took the derivative of t, if I take the derivative of t, because it's a unit vector, it's going to be perpendicular to t itself. But math is not elbow and hand. Math is prove. How could you prove this, Dr. Warren? How could you prove this? Well, this is the rough proof. Could you square both sides? Could you square both sides? Then the norm of t squared would be equal to 1. Now I've got to ask, does the norm of a squared equal a dot a? Does the norm of a squared equal a dot a? Does the norm of a squared equal a dot a? Okay, so this would say the same thing if I squared both sides. It'd be saying the same thing, that t dot t is always equal to 1. Is there a product rule for dot products? Okay, you have a quest coming up. Okay, is there a product rule? What's the product rule if I took the derivative of this side and took the derivative of that side? How many people like own this one? How many of you be like, Dr. Warner, I own that one? That would be 0. But on this side, I would get a t prime dot plus t dot t prime. Is the dot product commutative? Is the dot product commutative? So then this would be like 2 t dot t prime is equal to 0. Is 2 0? Is 2 0? No. So that means t dot t prime's got to be equal to 0, which means those two vectors have to be perpendicular to each other. And so we define capital N, which is the next basis vector, to be t prime of t. Now, it's not a unit vector. That's almost never a unit vector. But I want it to be a unit vector, so I would divide it by its, I want it to be a unit vector, so I would divide it by its norm. And this is my second basis vector. So now I've got a vector t that's perpendicular to n, and then I want another vector that's perpendicular to both of those. How could I do that? I got a vector t, it's perpendicular to n. How could I get another vector that's perpendicular to both of those? Cross product. And so that's what we do. We define b, the last one of these, to be equal to t cross n. We define b to be equal to t cross n. And in general, this is a horrible thing to do. In general, this is a horrible thing to do, unless the functions are super simple. But it's a really important coordinate system. So just don't look at your notes, don't look at your notes, don't look at your notes, don't look at me. I mean, look at me. Don't look at the board. Do not look at that board. How do you find capital T? Don't. How do you find capital? If I gave you a space curve, how would you find capital T? R prime divided by the, that's the way it's defined. How do you find capital N? How do you find capital N? Don't look at the board. T prime, you take the derivative of this, divided by the norm. How do you find your third vector? How do you find your third vector? T cross N. How many people have it down in theory? I mean, how many people like kind of understand what we're doing here? Okay, so now I just want to like show you why this is so important. At least give you a visual. So the university got cheap on me. Cheapskate. Okay. Oh, you got freaking kidding me. There's no passcode for this.
They might email this to you. I can set it up.
You go to Zoom. All Zoom meetings and recordings. Cloud recordings. We're gonna do this. We're gonna do this.
They gave you that, you have the password already copied to your computer.
I do?
Yeah, when you open them.
Oh, bless your heart. Never. Okay, so guys, they used to have a software package that they would let me use. Sorry, this is not.
What I'm trying to show here is they used to have Maple in
Look at that confused.
on the classroom machines, but they don't have that software anymore, I think because of cost. But Maple has a really nice vector calculus package, so I kind of wanted to show you this here, I'll just share my screen and let me come up here. We'll execute this, but this is kind of a crazy space curve. If you look here, what I've got up here, I've got this t times cosine of 3t, t times sine of 3t, and t squared minus 6 times t.
Could you guys take
Now
the derivative
imagine
of those?
having
Could
to
you take the
calculate
derivatives?
the t and b vectors for that. Remember that capital T is the space curve's derivative divided by the norm. Okay, then you got to calculate n, which is t prime, so you're taking the derivative of that mess divided by its norm, and then you got to take the cross product of t and capital N to get b. But notice I'll do this just to show you the horror. Maple's going to do it. There is t, horrible but not so horrible.
Just
Here
first
is
component,
n.
second.
Can you imagine
First
that
component,
nightmare?
second.
Can you imagine that nightmare? Trying to calculate it. And here is b. But what's even more fun is I can get
Why would you do
Maple
this?
to plot this for me, and you can see I'm running it between 0 and 3 pi, and I'm having it do 200 frames to show an animation. And so what we have here is you can kind of see it. It's a little hard to see the vectors. This vector right here is t. This is n, and this is b. And so what I'm going to do is I'm going to play the animation, and this is a fun curve. Imagine this being a roller coaster we just created. And again, the thing that's creating it is my space curve running between 0 and 3 pi. And now what I'm going to do is come down and you guys can watch this frame fly through on the curve. And what's such a much better frame to describe what the pilot's feeling than your IJK. I mean, your I would sit down here, your J would sit there, and your K would there. So let me just go ahead and do this. So you can see it moving around that curve. You can see it moving down there. You see how it's flying along my space curve. As we go through here, the tangent vector points to where I'm going, the n points to where I'm curving, and the b is describing how my pilot's wanting to move out of that osculating plane. So let me just do that again. Let me play that again. And you can see how this is moving, how the n is pointing, the green vector is pointing to where we're curving the most, t is pointing to where we're going, and my b up here is pointing to how I'm wanting to move away from that plane, how I'm wanting to move up. So I thought this would be a fun animation for us. So I'll stop sharing, and I'll stop recording, and you won't have to hear my boring voice.
Okay, does that help? I mean, does that help at least visually? I mean, does that give you a sense? Is it a lot of work? Is the TMB frame a lot of work? But do you think NASA would like that? I mean, do you think NASA would like to have that kind of perspective of what's happening with their shuttle, or with the I guess the shuttle's dead. Sorry. With going to Mars, do you think this would be important, like in modeling forces on things as stuff moves along? Fighter pilots, missiles. I mean, does all this make sense that this is relevant stuff? It's not easy to calculate. I mean, they're not easy to calculate. So I've got to give you guys functions that are really easy to take derivatives of, because then you got to take norms and square roots. But I found a way that I've never seen in any books to make it a lot easier to calculate the T and B frame at a point, okay? And we're gonna talk about that on Monday. We're gonna talk about that on Monday. Right now, you're gonna take a quest. Okay. So when you're done, you can go. When you're done, you can go. I'm just gonna pass them out along the roads as I go up. Just put them right here. Just put them right here when you're done, and I'll spray them on Lysol. I'm just kidding. Oh, bleach. If you get extra copies, just send them back. I just got it. Just pass that back. You're only allowed your brain, you're only on your brain and something to write with. Keep your eyes on your own work.